All right, today we're diving into something pretty groundbreaking in AI. It's an architecture that's making models faster, cheaper, and more powerful all at the same time. It's called Mixture of Experts, or MoE for short, and it's built on this brilliantly simple idea.
And that's pretty much the whole philosophy right there. I mean, think about it. Instead of firing up an entire massive AI brain for every single little question you ask, what if you could just switch on the specific parts you actually need? It's a total game changer. But to really get why it's so important, we have to look at the problem it's designed to solve.
And yeah, that brings us to maybe the biggest hurdle in AI right now. I like to call it the billion parameter problem. And it really all comes down to the massive hidden cost of making these incredible models so powerful.
I mean, we've all been blown away by what these huge models can do, right? But what you don't see is what's happening behind the curtain. Training and running them takes an absolutely insane amount of computational power. We're talking massive server farms, huge energy bills, and it all leads to slower response times. It's a simple rule. The bigger the model gets, the more expensive and the more sluggish it becomes.
So the big question is, how do we solve this? Well, this is exactly where a Mixture of Experts comes into the picture. It's a really elegant solution to this whole parameter problem. It offers a fundamentally smarter way for these AIs to actually think and get work done. Okay, so what is a Mixture of Experts model actually? Well, at its core, it's not one single, giant, do-everything network. Nope. Instead, it's more like a collection of smaller, specialized little networks. And we call these experts. So when you give it a task, the system is smart enough to route your request to just the one or two experts that are best suited for that specific job.
You know, this is probably the best analogy for it. A traditional AI model, it's like one single doctor who's forced to memorize every single medical textbook in existence. An MoE model, on the other hand, is like a top-tier hospital. You've got specialists for everything: a heart specialist, a brain specialist, a surgeon. You wouldn't ask all of them for advice on a common cold, right? Of course not. You go straight to the expert you need.
Okay, so that's the big idea. But how does this whole hospital of experts thing actually work? You know, on a technical level, let's break it down and kind of meet the team. So, the real magic here is a component called the gating network. Think of it like a super smart project manager or an air traffic controller. When a little piece of information, what we call a token, comes in, the gating network takes one look at it and basically asks, okay, who on my team is the best fit for this job? And then, bam, it sends that token to just one or two of the most relevant experts. They do their specialized thing, combine their results, and you get a final, super efficient answer. And this whole process creates a really important effect called sparsity. What this means is even though the total MoE model might have a huge number of parameters, we're talking trillions, spread across all its experts, for any single task, you're only using a tiny fraction of them. The rest of the model just stays quiet, not doing anything, which saves a ridiculous amount of energy and time. Okay. Here's another great way to picture the difference. A traditional model, we call it a dense model, is like making your entire company show up to every single meeting. Doesn't matter if it's about marketing or engineering or the budget, everyone has to be there. It's a colossal waste of time, right? But the MoE model, that's like a smart manager who just invites the 2 or 3 people who actually need to be in the room. It's just a fundamentally more efficient way to get things done.
All right, so we've got a smarter design. But what's the bottom line? What do we actually get out of it? Well, this is where we talk about the efficiency payoff. And believe me, the real-world benefits of this clever setup are just huge.
I mean, the difference in how much it costs to run these things is just staggering. This chart gives you a pretty good idea. To get the same level of performance, a dense model needs a massive amount of compute power. But the MoE model? It gets the same or sometimes even better results using just a tiny piece of that. And this isn't just a small incremental improvement. We're talking about a revolutionary leap forward in efficiency.
So the key takeaway is this: we get quicker answers because we're not lighting up the entire model for every single thought. We save a ton of money and energy on computing costs. And maybe the most amazing part, we can take all those savings and reinvest them into training even bigger, even more knowledgeable models for the same price tag. It lets us push the boundaries of what AI is even capable of.
But you know, this is way more than just a clever technical trick. This really signals a major shift in the entire philosophy of how we build artificial intelligence. For years, it felt like the only way to get better AI was just to build bigger and bigger models. Just throw more and more computing power at it. A total brute force approach. MoE completely changes that way of thinking. It proves that you can get to incredible scale and power, not just by being bigger, but by being smarter, by being selective. You know, kind of like our own brains work.
And so that leaves us with a really fascinating question, doesn't it? We might be stepping into a whole new era of AI, one where smart, efficient design is actually more important than just raw size. Maybe the future of AI isn't about building the biggest brain possible, but about building the one that knows how to use all of its parts in the most effective way.